So my name is Sarah Osborn, and I'm also here with Ulrike Yang, who you met this morning, to talk about Krylov solvers and algebraic multigrid in HYPRE. And we're both from Lawrence Livermore National Lab. So I'll first give an overview of what I'll be presenting on today. So first I'll start off with what are Krylov methods and why we are interested in using them. Then we'll have a hands-on portion to kind of explore some different Krylov methods in the HYPRE library. Then I'll discuss multigrid methods and also, kind of how does multigrid work. I'll give you an overview of some available open source algebraic multigrid software. And in particular, I'm really going to be focusing on the HYPRE software library. One of the unique features as a little preview of HYPRE is that it provides several different multigrid methods, but in particular, it provides different interfaces for you to specify your linear system. And then I will kind of end on some different multigrid solvers depending on whether you have a structured or an unstructured problem. And we'll also have some GPU considerations and we'll actually have a hands-on kind of before that. And then our final hands-on will be doing some CPU versus GPU performance studies. So I will dive right into some background. So the solution of systems of linear equations, and we're really thinking about large sparse systems here, is at the core of many scientific simulation codes. So we really need effective methods and code bases to accomplish this. And so y'all don't need to spend your time, kind of reinventing the wheel. So let us consider the problem of solving AX equals B, where again, A is a large sparse matrix of size n. And in this context, we could be thinking of maybe, n maybe is a million, couple billion degrees of freedom here. And so generally in this paradigm, we're kind of thinking that direct solvers are too expensive. There are some good direct solver implementations out there. We had a session on that this morning, but we're really going to be focusing on iterative solvers in this session. So a very simple iterative method is Richardson iteration, which we can see here. So basically what we do is we take an initial guess and then we add to it the residual, which is just b minus a times our current iterate. So now if we look at the corresponding error equation, we can see that this is going to converge if we kind of have, so this is the identity matrix here, I minus a. And so this is basically telling us that this is going to converge if we kind of have an matrix that is nice, where I'm kind of glossing over some of the details of what nice means. And basically, if A is not a particularly nice matrix, then this simple iteration is not going to converge. So that's kind of the motivation for why we now want to consider a preconditioner. So basically, the idea of a preconditioner, which we're calling B here, is we can multiply our residual by this preconditioner or apply our preconditioner to it. And then we now look at our corresponding error term, and we now see that it is looking at the identity matrix minus b times a. So then basically we want this to be nearly the identity. So we're looking for a preconditioner that kind of mimics the operation of A inverse. So now we're going to, with our preconditioner, potentially get a much better convergence rate. So some very simple preconditioners, we can consider Jacobi, which is just the inverse of the diagonal of A. And the true Richardson method is actually, we have a preconditioner of lambda I. So in my equations up there, I was just assuming lambda was equal to 1. So now let's actually look at some Krylov solvers. So let's consider the iterative step as we had it written before. So we have an initial guess, then we add in some preconditioner times our residual. Now if we start thinking about starting with n equals 0 and we keep iterating, we can see how we can rewrite this equation to be a linear combination of these vectors. And now if we look into this in a bit more detail, we can see that we have these polynomials b times a to the power of I times our vector, our preconditioner times our right-hand side. So now from this, we can deduce that our approximation x to the n plus 1 is going to live in this space that's generated by these polynomials. And we call this our Krylov space. So now if we want to be able to find a good approximate solution within this space, we can optimize the following norm written here. And basically we can, find the best alpha to get us closest to our solution. So now to do this, we want to be working in an orthonormal basis. So we're going to orthonormalize the vectors to construct our new basis. And then we're going to solve this minimization problem with our new, more robust space. And we call these Q sub I our search directions. So that's the basic idea of the generalized minimal residual method, or GMRes. Now we can, oh, nope, we can't. We're going to speak a little bit more about GMRes before I move on. So we want to think about how we're going to implement this, and basically how we're going to implement this in a way that we can take advantage of our HPC computing. So we want to be able to, have an efficient parallelized version. So let's look at some of the components. So overall, everything is pretty relatively, simple operations. We have some inner products and norms. Those are going to involve global reductions. We have some vector updates, which are, embarrassingly parallel. We have some matvecs, so those are going to involve some nearest neighbor updates. And then finally, we have our application of our preconditioner. So that can be something very simple, like what we just saw on the previous slide, or that can get fairly complicated. But we'll go into that later in the talk. So now imagine as we're building up our Krylov space, the way I had it written is we're having to keep track of all of these Q sub i's, our search directions. So this can become pretty memory intensive. So we have a variant that is called restarted GMRes, or GMRes K, which basically after K iterations, we're going to throw away all of those previously generated Q sub i's and just start again using our most recent approximation. And there are also several variants attempting to reduce or help overlap the communication within the GMRes algorithm. But again, I'm not going to go into any of those details here. All right, so now there are several other options for Krylov solvers, so I'm going to mention a couple of more. So if we have a symmetric positive definite system, we can use the conjugate gradient method. And so similar to GMRes, it's going to orthogonalize, kind of something using a slightly different norm. We also have this additional property that instead of having to build up the entire Krylov space, we can rely on a 3-term recurrence formula. So we don't have to keep track of all of those Q sub i's like we had to in GMRes. And overall, each CG iteration is cheaper, as we only need 2 inner products and a norm per iteration. So because conjugate gradient does possess some really nice properties, folks have come up with another method for non-symmetric matrices, because CG is limited to the certain type of problem it can be applied to. So similar to CG, by CG stab uses this 3-term recurrence relation, but it does not have this orthogonality property. So when it works, it usually works really well. However, it can break down in some cases. So GMRes tends to be more robust overall, but by CJAB is, more, it's less expensive. So those are some of our Krylov methods that we have implemented in the HYPRE library. So I am going to let y'all go through a set of hands-on experiments. I put the link in the Slack channel. So what I'd like y'all to do is go through kind of the first set of runs. So they're grouped into 3 sets on that page. And basically here you're going to be experimenting with HYPRE's GMRes, preconditioned conjugate gradient, and by CG stab, and also play around with that restart parameter for GMRes. So if you go to, let me see if I can switch over relatively easily. All right. So if you go to the link that's in the Slack channel, it should take you here. And basically, I've assumed that you've already followed those setup instructions at one of the previous sessions today, and then you also need to follow those same set of sessions and go ahead and grab yourself an interactive session, and then you'll move into the correct directory that contains the HYPRE executables. And so just to talk through kind of the problem that we're solving while y'all are getting your, getting in line for the queue, let's see. So our favorite problem of today is solving the Poisson equation. Let's see, and then we are going to be performing experiments first with the executable called IJ. So this is using HYPRE's unstructured interface. And the first command you'll run is just getting some more information about the available command line options for this particular executable. So I can talk through some of those, but basically you're able to kind of choose which problem you want. You're able to choose the size of the problem, and then you can also play around with different solver choices. All right, so I'm just going to let y'all have maybe a little less than 10 minutes to work through these exercises, and I'll be here and Ulrike is here to take any questions that you have, and I will come back. Get started back. Beautiful. All right. All right, so we've done some investigations with using different Krylov solvers and some more simple preconditioners, but now let's start talking about multigrid and really understanding the reason why multigrid is so popular. You know, why are we having 2 sessions of it today? And the reasons why they're so commonly used is because they're optimal methods. Now, in the sense, I'm meaning optimal by if we're solving for n unknowns, then we can solve it in order of n operations. And so because of this, there's really good scaling potential, particularly in the weak scaling sense. So if we look at this idealized graphic here, which is considering a weak scaling study, you know, so here as a reminder, we are increasing the number of processors as well as growing the problem size. And ideally, we would like constant solution time in this framework. But if we just stick with the more kind of classical methods, just like Krylov methods, like we saw in the hands-on exercises that you were just working through, we see oftentimes that the number of iterations is going to grow as our problem size grows. So even if we throw more computational resources at our problem, it's still going to take overall longer time to solution. So that's where multigrid methods come in. So with a multigrid method, you know, in theory, we can actually achieve this constant solution time, or at least, you know, close to it. Now let's briefly go through some of how multigrid actually works. So in this cartoon view here, imagine that we have a 2-dimensional Laplacian problem. And since we're thinking about an iterative method, suppose we're going to have an initial guess and we're going to plot the error, which is what's shown here. So we're going to plot the difference between our initial guess and the exact solution, and it might look something like this. Now we're going to notice that if we apply a few iterations of some simple method like a Jacobi iteration, we're going to be able to smooth that error. So basically we're going to be able to decrease that high frequency error with the relatively few iterations of something relatively inexpensive. But if we kept grinding away with Jacobi or something like it, we would really never get it to smooth all of the error. So instead, and kind of where the magic of multigrid comes in, is we're going to instead project that error to a coarser grid. And we can accurately do this because our error has been smoothed. And so now we can either solve our problem on this smaller grid, or we can keep restricting into coarser and coarser grids and keep doing this smoothing process as we go down. Then we're going to interpolate our solution back up and correct our current solution. And at the end of this process, we make very rapid progress toward our overall solution. And so in practice, like I mentioned, we would actually go down several levels and come back up. We call this a V cycle. There are other kind of more creative cycles that one can do. However, we typically do a V cycle because in parallel, it scales the best. So I've walked through this very much kind of with using a geometric picture, but we can do this in an algebraic sense, where we're only given a system of equations. Then algebraic multigrid does not rely on actual grids. It uses the facts that you have just a bunch of coefficients in a matrix, and it uses that information to build up our coarser grids, where we're now saying kind of grids in air quotes. So algebraic multigrid has two main phases. We have a setup phase and then a solve phase. So in our setup phase, we are constructing our coarse grids, again, kind of air quotes, where we're using our graph representation of our matrix to determine the set of coefficients which we should restrict to our coarser level. In this phase, we're also defining our interpolation operator, which is, under figuring out kind of the right way to interpolate our error. And we're also determining our restriction operator. And since we're typically working with symmetric matrices, we're just going to use the transpose of our interpolation operator. And that also works if you're slightly non-symmetric as well. Then our coarse operators are determined through a Galerkin product. So this is this triple matrix product RAP. Then in the solve phase, again, this is what we're terming our V cycle. We first apply our smoother, then we compute our residual, we restrict it to our next level, then we either solve here or we keep going to kind of deepen our V. Then we're going to interpolate back up, add those interpolated values back to our approximation, and relax again. So that's really the basics of algebraic multigrid. One thing to note when we're thinking of performance is, especially in this solve phase, the primary computations are matrix vector products. So ensuring that we have an effective implementation, which relies on oftentimes having a good way to have a good way for our underlying data storage of our linear system is going to be key for performance. Now, so there are several open source options for different multigrid implementations. In Trilinos, there's Mulu, and some of y'all maybe caught the session earlier today, which provides smoothed aggregation type algebraic multigrid. PETSC has GAMG, which uses a mixture of geometric and algebraic components. And then HYPRE, which is what I'm representing here today, features several different algebraic multigrid solvers, and we also have some specialized solvers for things like Maxwell equations. So all of these options really provide different flavors of multigrid, and depending on your problem, one package might be preferable to the other, but all are high quality, performant implementations. So now I'm going to go into more details of the HYPRE library. So HYPRE provides multigrid solvers for both structured and unstructured problems. And it's used in many applications. We have a few here on the slide with some pretty pictures. And this graph demonstrates that, like the theory tells us that we can actually achieve good weak scaling using algebraic multigrid. So as I mentioned before, a unique property of HYPRE is this notion of a conceptual linear system interface. And we call them conceptual because the idea is we want a user to be able to look at their linear system interface similar to how they actually look at their problem of interest. So if we look at some of these examples on the far left, would be an example of if you're maybe doing a finite difference method, finite volume method to discretize your problem. You have a notion of a physical grid. You have maybe a stencil on that grid and actual coefficients on that stencil. And then you can provide that additional information to HYPRE, which can then in turn use that information for using a very particular underlying data structure layout and also provide you with a specialized solver for this interface. And I'll go into more details later. But also at the other end of the spectrum, we just have kind of a regular, how you describe your matrix A just in terms of row column coefficients. So to reiterate just some of the key points about why HYPRE supports these multiple interfaces, it provides a more natural view of your linear system depending on your problem that you are interested in solving. It eases some of the coding burden by eliminating this need to map to create a matrix based on rows and columns. It provides more efficient and scalable linear solvers. And the way it can do this is because under the hood it uses more effective data storage schemes and more efficient computational kernels. HYPRE supports 3 main interfaces. Struct or structured grid is appropriate when you have logically rectangular grids with a fixed stencil pattern. We also have semi-struct or S-struct. And so this allows you to describe more complicated settings. So these are problems where you have they're mostly structured, but not entirely. So some examples of when this is used is if you have a block structured grid, or you're doing something maybe using AMRX of structured adaptive mesh refinement grids, and even finite element problems. And then we have just the classical version, IJ, where you're just setting up your matrix by rows and columns. And the IJ interface is probably the most widely used. Now I'll review some of the algebraic multigrid algorithms and design details for our structured and unstructured solvers in HYPRE. So on the unstructured side, first, BoomerAMG is our unstructured method, and it's really the workhorse of HYPRE. Lots of folks use it for a lot of different applications. So it features many different options, so you're able to customize this solver for your particular problem of interest. You can choose the different coarsening, interpolation, and relaxation schemes. So there are a lot of knobs to adjust, but the default values have been chosen with care to generally work well for most problems. But there are a lot of things you can just adjust for your particular problem of interest. And let's see, so it can also be used through PETSC and Trilinos, and it also has GPU support. Now, something to keep in mind is when we are computing our coarse grids using RAP, it can have unwanted side effects. So even if our original matrix is very sparse, as we're computing our coarse grids with our triple product, this can cause stencil growth, where our number of non-zeros per row increases. So we can see this becoming an issue if we look at the communication pattern where the different color indicates messages being sent and received. And so we see this communication increasing as we're coarsening. And this increased communication will cause performance degradation. So we can assess this by considering the operator complexity. So this is where we compute the number of non-zeros across all of our levels in our multigrid hierarchy divided by the number of non-zeros in our fine level. So ideally, we want this to be less than 2 and close to 1, as this is going to affect our flop count and memory. So we can control this complexity in a few ways. One is with aggressive coarsening, where essentially we coarsen twice. But we need to do all of these things with care, as it can cause convergence, deterioration, and we don't want a very fast, effective method, but that doesn't converge well. So there's kind of a trade-off here. And we'll play around with that aggressive coarsening scheme in our hands-on exercises. So now let's look at the data structure for the unstructured linear system in HYPRE. So it is based on a compressed sparse row data format. So it's distributed over processes row-wise, like shown in the figure here. And it's actually stored as 2 CSR matrices. So the first one contains the local coefficients connecting to the local column indices. And then the second stores the coefficients of if your column indice is pointing to off-processor rows. Then we also need to keep track of the mapping between the local and global column indices for the second off-D CSR matrix. So with this data structure, there is a lot of indirect addressing and computation of relationships between processors. So it's less effective than our structured interface, but we can't always have structured in our problems, so we kind of do the best that we can. However, when we do have structure in our problem, we can really leverage that using specific methods that take advantage of the fact that there is structure and we do have these stencils associated with our problem. So they can really produce inexpensive and fast solvers. So to do a bit more of a deep dive into our structured interface, so we have 2 main solvers here. So we have SMG, which uses plane smoothing. So it's a more expensive method, yet it's very robust. So there have been some use cases where this is really the only solver that will work for a particular problem. Then PFMG is probably our most efficient solver. It uses a simple pointwise smoother, which makes it very efficient, per V cycle, but it's not quite as robust as SMG. But the nice feature about both of these solvers is there's limited stencil growth. So we aren't getting that increase it's bounded, the number of non-zeros per row as we're coarsening. So we don't have that issue like we were previously discussing for the structured case. Let's see, and these methods can also be used on GPUs as well. We have several underlying GPU programming model options. Now let's look into the PFMG in more detail to better understand why the stencils don't grow. So here our matrix A is defined in terms of grids and stencils, and then this method uses semi-coarsening. So it uses a simple 2-point interpolation, and this is what allows it to limit the stencil growth, which again is important for the performance as we coarsen. There's also a non-Galerkin approach, which can use additional information to actually preserve the stencil size as you coarsen. And this is really our most efficient solver for if you have, the right type of problem. Now to look more at the underlying data structure of the structured interface. So we have a global D-dimensional index space, and then we are able to define these boxes, which is just a collection of cell-centered indices, and you kind of describe it by your lower and upper corners here. And then your grid is then just described in terms of these boxes, where you can use an arbitrary union of boxes. Then the matrix coefficients are defined via stencils. So our example here is just using constant coefficients, but we can also have variable coefficients. Then to look a little bit more into the data structure. So the user provides the definition of the stencil and the grid boxes definition. And then HYPRE under the hood generates what we term a data space, which is our grid boxes plus these ghost layers. And so these are important because this allows us to transfer information across the different boxes. Then the actual data is stored in the following way, that for each stencil entry, all of our entries are stored contiguously for each box. And the consequence of this data storage is that we can have very effective loops over the boxes. All right, so that was kind of a deep dive into some of the solvers and underlying data storage of the structured and unstructured interface. And before we get to our hands-on, just one more kind of note is I have been talking about algebraic multigrid primarily as a solver, but typically in practice, algebraic multigrid methods are really used as preconditioners to accelerate Krylov methods. And this will allow us to have additional performance improvements. So just one more weak scaling, one more weak scaling study. Again, this is a diffusion problem, but here we have our coefficient kappa here has really large jumps, so it makes it a harder problem. And we apply just preconditioned, diagonally preconditioned conjugate gradient, our BoomerAMG, which is our unstructured solver, and our PFMG, which is our structured solver to this problem. And we can see that by far, our solve time is the smallest with PFMG, but we can see that both multigrid preconditioned methods outperform just that diagonally preconditioned conjugate gradient method. So this kind of shows the power of multigrid as a preconditioner. All right, so now I will break and have y'all go through the second set of runs, which is using HYPRE's algebraic multigrid solver as a solver, and then as a preconditioner, you'll also perform some weak scaling experiments, and you'll also get to see the difference between the BoomerAMG, the unstructured, versus our structured solver, PFMG. All right, so again, please let us know if you have any questions or issues. Let's see, I will then show where you should start. So kind of start in this algebraic multigrid section, but then end before the third set, which is the GPU. All right, let's see. I think we have plenty of time, so let's say 10 minutes. I'll say. All right, so I am going to, thank you. I'm going to talk through our very last section, and then we're gonna end, oh, we want this, yes, okay. All right, so in this last section, I'm going to focus more on our porting of HYPRE to GPUs, some of the changes that had to be made, and then I'm going to present some experimental results kind of comparing CPU, GPU, and structured, unstructured. And then we're going to have our final set of hands-on exercises. So as you all know, for good performance on GPUs, you want to have regular compute patterns. And so this really posed a challenge for the unstructured solvers, as well as kind of for multigrid methods in general with decreasing level sizes, so as we're thinking about our coarser grids. So in HYPRE, we have taken different strategies for our different interfaces. So for the structured interface and solvers, this was by design just much simpler because basically all of the data operation was done within what in HYPRE they're termed these box loops. So it was very simple. It was easier to switch out a new programming model. So we have CUDA, HYPRE, Raja, Cocos, and even SYCL, that may be still kind of work in progress, for the structured interface. So once that insertion of the programming models was done, then basically that interface, the full algorithm could then be run on these different architectures. Now for the unstructured interface and solvers based on that CSR underlying matrix data structure, things were more complicated. So the first step was kind of modularizing the compute code into kind of making it into smaller, chunks and kernels that then those kernels could be ported to CUDA first for the NVIDIA GPUs. So that was kind of the first step in porting this portion of HYPRE. Then those CUDA kernels were converted to HIP for the AMD GPUs and SYCL for the Intel GPUs. And then really where a lot of the research was done was in actually having to develop new algorithms and implementations for the portions that were not suitable for GPUs. So in particular, this was coming up with different interpolation operators and smoothers. And so something to keep in mind when we're thinking about the experiments is that there are now different defaults for running HYPRE's multigrid solvers on CPU and GPU. And also we have some various specialized solvers for different types of problems in HYPRE, and those are all built on BoomerAMG, that unstructured solver. So really any improvement to the performance of BoomerAMG and any porting effort of BoomerAMG to GPUs also benefits all of these specialized solvers because they are all kind of sit on top of BoomerAMG. All right, so now I'm going to present some results. So this was a weak scaling study that's comparing the performance of BoomerAMG, our unstructured solver, and PFMG, our structured solver, but these were both used as preconditioners for the conjugate gradient method on both CPU and GPU. So note that these experiments were performed on Theta GPU. This is the same compute nodes that y'all have been using for your hands-on today. For the GPU, we were just using one of the NVIDIA A100 GPU for the GPU runs, and then for the CPU, we were using 6 MPI task. So if we look at these results in more detail, so the dashed lines are the CPU runtime, and then the solid lines, that's the S word, are for the GPUs, and then red is our structured multigrid PFMG, and the blue is AMG. So to look at some of these speed ups. And then again, like I was mentioning before, so these were both for the CPU and GPU, these were tuned to use the optimal settings, which are different on the CPU versus the GPU. So that's just kind of something to keep in mind when you're considering the comparisons. So we see that the structured multigrid method performs significantly better than the unstructured on the CPU. And that speed up is even better when we start to consider the GPU. And those actual speed up numbers are listed here in the boxes. So just a few caveats though, as we are looking at this performance and kind of in general when we're thinking about these weak scaling studies. So in this instance, we are just running on a single GPU. So in a scenario when we're considering multiple GPUs, we're going to incur some cost of the MPI communication between GPUs. So we would expect our GPU performance to still be better than our CPU, but we're maybe not going to be expecting, this nearly 30x speed up if we're considering, a multi-GPU run. Also, something to keep in mind with these type of experiments that we're demonstrating here is we're really kind of trying to flex our muscles for demonstrating the potential of these solvers on CPU and really on GPU. The caveat is kind of in practice when we're actually thinking about running, an application that has a deep software stack, you're going to be using your memory and things for other portions of the computing process. So you're not going to probably be able to devote, all of your compute allocation just for the linear solve. So that's just kind of something to keep in mind. So this is really just demonstrating, that we can run HYPRE in this large scale setting, but potentially in your real world applications, you're probably not going to be executing runs in this regime. Your problem potentially could be more in this kind of smaller scale or medium scale where you don't see these dramatic increases in the GPU. Just as kind of a word of warning, but overall, we're pretty pleased with these speedups that folks are able to accomplish. Then this is the same weak scaling study, but it's just considering this two phases of multigrid separately. So we have our setup times on the left and our solve times on the right. And so just kind of the things to note here is that we really see the improvement with our structured over our unstructured, especially in the setup time. And again, in the solve time, we still see some performance. And again, the solve time is pretty much dominated by those matrix vector computations. All right, so I am actually going to pause here. If there are any questions over what I've presented, if anyone has questions on that, I'm happy to take those. Yes, please.
Maybe it was a bit lost, but like in the, I don't fully understand why the difference is so dramatic even the CPU, right? Because it seems like it is scaling much better, because this is the solve time, and then the bottom is the number of CPU. What is that? The exact.
You're asking why the difference is so big?
Yeah.
Yeah.
Like the slope. I don't know.
Okay.
I would guess that it's requiring more communication, maybe, or.
The setup time.
Yeah, do you want to explain it?
Maybe I'm not understanding the question as well as you are.
So the reason the difference is so big is, my understanding is because you're asking why is the difference so big between the two, right?
These two.
Yeah, the thing is for the setup times, for the unstructured one, it's really difficult to do the setups. Part of the reason is the way the interpolation is. You probably remember when Sarah talked about PFMG, we have very simple interpolation, only 2 points. You know, we also have the restricted stance and we don't have the groups. You see all of this in the unstructured code, what happens, and because we have to actually look for our neighbors, so we have to find neighbors of neighbors. So there's a lot of communication going on in the setup. Once we have the neighbors, we don't need to do that anymore. So that's why in the solve time, you don't have that issue. You don't have that issue for PFMG because we already know the grids. So we already know our neighbors, right? So it's kind of cheating a bit. That's the reason why there's such a big difference, right?
Yeah, thanks for
There are more, but that's the main reason. So.
All right, so now I'll let y'all go through the last set of the hands-on experiments. And here you'll run on both the CPU and GPU, and to be able to see, some of the potential speed up to be gained when you're executing the algebraic multigrid on GPUs. And then at the what? Oh, okay. Okay, and then there's also kind of some additional exercises at the very bottom of the page if you have extra time and you wanna work through those. And I guess
There is a problem. I made a mistake when I put these hands-on exercises for GPU and CPU together. I mean, it's not really a mistake, but there is some inconsistency. So I don't know if you guys run it and you see something. Yeah. I'll be curious to see if any of you figures it out.
thanks.